Hello again, it's Mr. P with our second segment on sound. So in our first segment we had discussed certain aspects of sound like frequency, pitch, intensity, loudness, and other characteristics of sound. In this segment we're going to talk about more characteristics of sound, so more about how our how we perceive the sound. Okay, and a few more aspects of sound. So remember, this would be the second segment for your e-learning for April 15th, Wednesday, and section 17.4. So in the last segment we talked about there's a range of frequencies that we as humans are able to hear. At the low end, 20 hertz. At the high end, 20,000 hertz. Remember, frequencies related to pitch. So the lower the frequency, the lower the pitch we hear. The higher the frequency, the higher the pitch we hear. All right, so we said, here it says 20 hertz to 20,000 hertz. So that's ideal. Okay, so as we get older, a lot of times that range gets narrower because we're not able to hear as great of a range of frequencies. Remember, the range of frequencies we can hear, depends on the health of our ears, our age, and so forth. So we said 20s at the low end. I'm going to go ahead and play a tone here at 100 hertz, which is toward the lower end, but not at the not at the extreme lower end. So that would be 100 hertz. So let's go toward the higher end of the scale, and this would be 10,000 hertz. Again, a lot higher frequency, so we should expect a lower pitch. So if we hear that, we should expect a higher pitch. So higher frequency, higher pitch that we hear. Okay, so we can see the difference between 100 hertz, really low frequency, low pitch, and then 10,000 hertz, very high frequency, high pitch. Okay, it kind of gives you an idea of the range that we're able to hear. So some terminology. So infrasound. Okay, this would be sound that are at frequencies that are lower than most people can hear. So lower than that 20 hertz. So like seismic waves from like an earthquake or an explosion. Whales. Okay, so whales communicate with sound, and sound waves that they emit are lower. Okay, we can't hear them because they're lower than that 20 hertz. Ultrasound, be it sound that occurs at frequencies that are higher than most people can hear. So higher than that 20,000 hertz. Some practical examples of that, places we might have heard ultrasound. So like ultrasound imaging, like in terms of a medical application. So basically what happens is computer software uses short pulses of ultrasound. Remember, ultrasound has high frequency, so short pulses, okay, we're thinking of short wavelengths, right? Because shorter wavelengths go with higher frequency. So basically these pulses bounce off different structures in the body and organs, and the result is basically a picture or map of the body is formed, and we're able to see more clearly what's going on. Sonar, okay, another application there. So basically, sonar is a technique for determining the distance to objects underwater by emitting sound waves and measuring the time delay of the returning echo. So they can determine how far things are away from a ship, for example, like how deep something is below the surface of the water, by how long it takes the sound waves to travel to the object and return back to the ship. Okay, so that's another practical example is sonar. Let's continue here. Okay, so let's look at something we call the Doppler effect. Again, this has to do with our perception of sound. So the Doppler effect is a change in the frequency of the sound caused by the motion of the sound source the motion of the listener or both. Okay, so frequency can change if the source of the sound is moving, if the listener is moving, or if both happen to be moving. All right, so let me show you and actually let you hear what the Doppler effect sounds like. So first of all, let's just talk about what's going on in the diagram here. So observer A, okay, we can see a police car with the siren going that's traveling to the right here. So away from observer A and toward observer B. So observer A is hearing a lower pitched sound than observer B because the wavefronts are further apart for observer A. Remember, longer wavelengths mean lower frequency. So as a police car travels away from observer A, there's longer wavelengths and lower frequency, and that frequency gets lower for observer A as the car gets further away. As the car gets closer to observer B is going to hear higher and higher frequencies because there are shorter and shorter wavelengths. So here's what the Doppler effect sounds like. So it's going to be as, let's say a siren is moving towards you and then moving away. Okay. So notice the increase in frequency as it moves toward us. And then now it starts to move away, and as the source moves away, we hear a lower and lower and lower frequency. Okay, so that would be an example of the Doppler effect. So as the sound source, maybe a siren, moves toward us, we hear higher and higher frequency. As it moves away from us, we hear lower and lower frequency as those wavelengths increase or spread out. All right, so again, we'll look at more about how we interpret sound, how our body interprets sound. So obviously, we're able to hear through our ears, which collect the sound and transmit it to the brain, and the brain interprets it as a certain frequency, a certain loudness, etc. So the ear is very complex. Okay, there's different parts of the ear. You got the outer ear, the middle ear, the inner ear, and they all have different functions. Okay, so outer ear, the middle ear, and the inner ear. So we'll look at a diagram here in just a second. So the outer ear gathers and forces sound into the middle ear, which receives and amplifies. So amplifies basically makes the sound louder, amplifies the vibrations. The inner ear uses the nerve endings to sense the vibrations and send signals to the brain. So outer ear gathers the sound, forces it into the middle ear. The inner ear receives that sound and amplifies the vibrations or gives them more energy. Okay, and then the inner ear uses the nerve endings to sense these vibrations, and then those signals are sent to the brain, and our brain interprets the sound to be a certain frequency and a certain intensity, and so forth. Okay, so we can see a diagram of the ear. So again, outer ear collects the sound, forces it into the middle ear, right? The inner ear amplifies the sound. Okay, then it goes to the inner ear, okay, where those nerve endings send signals to the brain, like the auditory nerve. Okay, that sends signals to the brain, and that's how our brain is able to interpret sound. Okay, so again, that's just a diagram of the ear and showing you the different parts of the ear. All right, so let's go back to our notes here, and we'll continue to look at how we perceive sound. So, how sound is reproduced. Okay, so as far as recording sound, okay, like we're talking about like recording music and so forth, sound is recorded by converting sound waves into electronic signals, okay, that can be processed and stored. So sound is reproduced by converting the signals back into sound waves. Okay, so sound is recorded by converting the sound waves to electronic signals, and then those signals are in turn converted back to sound waves to reproduce the sound. So as far as music goes, most musical instruments vary pitch by changing the frequency of standing waves. All right, so again, we talked about in our last segment, say if we're talking about instruments that have tubes, for example, that longer tubes produce longer standing waves, which means lower pitch than a shorter tube, which would produce a shorter wave and a higher pitch or higher frequency. Okay, so that's again what we're referring to there. The concept of resonance as it relates to sound, okay, is the response of a standing wave to another wave of the same frequency. Okay, so musical instruments use resonance to amplify sound. Remember, amplify basically means to make louder, increase the intensity, the amplitude of the wave, so that increases the energy of the wave, that increases the loudness of the sound. So one wave can push another wave to a higher amplitude, which means we got constructive interference going on. So remember, if we have two sound waves that interfere constructively, remember that would mean like their peaks line up, their peaks occur at the same time, we would end up with a resulting wave that has a much greater amplitude, okay, which would mean louder sound, greater intensity. Okay, so as I said here, resonance can produce a dramatic increase in amplitude or an increase in the loudness of the intensity of the sound. So if we think about this in terms of a musical performance, okay, sometimes we don't want the resonance, the reverberations. So there are what we call sound absorbing tiles, okay, that absorb unwanted reflections, and we can also have curved panels, let's say above the stage. These actually direct the sound toward the audience, right? So we can hear the sound. Okay, so those are some applications of what we're talking about with resonance. So sound absorbing tiles, they absorb unwanted reflections, and then we also have panels that gather the sound and kind of direct it toward the audience. So if we look at a picture of what we're talking about here, so we can see by the stage we have these curved panels, right, that's directing the sound toward the audience, and then we got the sound absorbing panels on the wall. Again, those are absorbing all the echoes that we don't want to hear. All right, so that's just kind of a practical example of resonance, okay, and how resonance occurs in a musical performance, for example. And this is Mr. P signing off until next time.